For decades, scientists said this couldn't happen. They said the San Andreas Fault was built differently, that it could only release its energy one way, violently, suddenly, catastrophically. They were wrong. And the proof was sitting in 9-year-old data the whole time, waiting for a machine smart enough to see it. To understand why this matters, you have to understand what kind of fault the San Andreas actually is. It runs roughly 750 miles through California, from the Salton Sea in the south, up through the Bay Area, and out toward Cape Mendocino in the north. It marks the boundary between two of the largest tectonic plates on the planet, the Pacific Plate and the North American Plate, sliding past each other horizontally at a rate of about 2 inches a year, roughly the speed your fingernails grow. Geologists call this a strike-slip fault, which simply means the two sides are grinding sideways past one another rather than one plate diving beneath the other. That distinction is the entire reason today's story is such a big deal. For most of modern seismology's history, researchers believed strike-slip faults like the San Andreas had one dominant way of releasing built-up stress, and that was through sudden damaging ruptures, the kind that produce the earthquakes everyone pictures when they hear the fault's name. The 1906 San Francisco earthquake is the textbook example, an estimated magnitude 7.9 event that tore through nearly 300 miles of the northern segment, and, combined with the fires that followed, killed roughly 3,000 people and left more than half the city homeless. Further south, the fault last ruptured in a major way in 1857, the Fort Tejon earthquake, also near magnitude at 7.9, breaking almost 200 miles of the southern section near what is now Los Angeles County. These are the events that shaped how an entire field of science understood this fault. Sudden, violent, unmistakable. But there was another kind of fault behavior that scientists had already documented elsewhere on Earth, something almost the opposite of a sudden rupture. It's called a slow slip event, and for years it was studied almost exclusively along subduction zones, places where one tectonic plate is forced beneath another. Researchers found clear evidence of it in Cascadia, off the coast of Washington and Oregon, and in similar settings in Japan, Mexico, and New Zealand. In a slow slip event, a section of fault moves the same distance it might during a small earthquake. But instead of that motion happening in seconds, it stretches out over hours, days, or even weeks. No violent shaking, no dramatic jolt on a seismograph, just a slow, silent drift that releases stress almost invisibly. In those subduction zone settings, scientists eventually discovered something even stranger tied to slow slip, a phenomenon called episodic tremor and slip, where the quiet ground movement is accompanied by a faint, continuous seismic hum, completely distinct from the sharp, sudden signal of a normal earthquake. That hum, called tremor, doesn't look like much on a standard seismogram. It doesn't spike, it doesn't jolt, it just persists, low and steady for hours or days, almost like the fault is breathing instead of snapping. Researchers spent years learning to recognize that signature in places like Cascadia, and it became one of the clearest fingerprints scientists had for identifying a genuine slow slip episode versus ordinary background noise. The question that lingered for a long time afterward was whether anything like that same fingerprint could ever show up on a fault built the way the San Andreas is built, sliding sideways instead of diving downward. For a long time, the working assumption was that this kind of quiet, gradual slip simply didn't happen on strike-slip faults the way it happened on subduction zones. The physics seemed different enough that many researchers considered it, in the words used by scientists who study this exact question, theoretically unlikely at best. If a fault system like the San Andreas released stress almost exclusively through sudden ruptures, then the entire logic of hazard modeling made a certain kind of sense. Watch for locked segments, calculate how long it's been since they last broke, and estimate how much strain has built up in the meantime. That was the framework. That was the assumption baked into decades of earthquake science. Then a research team went looking in a place seismologists have been staring at for almost 50 years, and they used a tool nobody had access to until recently. That place is Parkfield, a small stretch of central California that has earned an unusual nickname among scientists, the earthquake capital of the world. It isn't called that because Parkfield produces the biggest earthquakes. It's called that because it produces small to moderate earthquakes with striking regularity, magnitude 6 events roughly every 22 years, going back to the 1850s. That regularity made Parkfield the most heavily instrumented stretch of fault on the entire planet. Since the 1970s, the United States Geological Survey and a rotating cast of university researchers have buried boreholes, planted strain meters, and installed dense GPS networks specifically so they could catch a Parkfield earthquake in the act, before, during, and after, and use that data to understand the mechanics driving the rest of the fault. The town itself is tiny, little more than a handful of buildings surrounded by dry, rolling ranch land, but scientifically it punches far above its size. Researchers picked Parkfield in the first place because 6 successive magnitude, 6 earthquakes struck the same stretch of fault at unusually regular intervals between 1857 and 1966, spaced anywhere from 12 to 32 years apart, averaging out to roughly every 22 years. That kind of repeatability is almost unheard of in earthquake science, and it turned Parkfield into the closest thing seismology has to a controlled experiment, a place where researchers could set up equipment in advance, wait, and reasonably expect the fault itself to eventually cooperate. In 2004, it did exactly that, delivering a moderate earthquake that arrived within the window. Scientists had projected, even if the surrounding prediction effort never achieved the precision researchers originally hoped for. The lesson from that experience wasn't that earthquake prediction had failed outright. It was that the fault was more complicated than the original models assumed, and that lesson is part of what set the stage for everything researchers are uncovering now. Some of the most sensitive instruments in that network are called borehole strain meters, devices buried hundreds of feet underground that are precise enough to detect distortion in the surrounding rock, caused by something as subtle as ocean tides pulling on the crust from hundreds of miles away. 4 of these strain meters sit in and around Parkfield, and starting back in 2009, they were quietly logging continuous data day after day, year after year, long before anyone knew exactly what they might eventually reveal. That data collection ran through 2016, generating an enormous archive of raw strain measurements sitting in research databases, technically available, but practically almost impossible to comb through by hand, with the kind of precision needed to catch something as faint as a slow slip signal on a strike-slip fault. That's where the story sat for years. The data existed, the question existed, but the tools to actually answer the question at scale didn't exist yet, not in a form anyone had fully applied to this particular problem. In 2026, a research team led by Dr. Zara Zali at the GFZ Helmholtz Center for Geosciences in Germany, working alongside colleagues from EarthScope and Stanford University, decided to go back through that 9-year-old archive with a completely different kind of tool, artificial intelligence. Specifically, they built a deep learning system designed to comb through the continuous strain records looking for a very particular signature, the kind of subtle, sustained deformation pattern a slow slip event would leave behind, distinct from noise, distinct from ordinary background creep, distinct from the countless small disturbances that show up in geophysical data for reasons that have nothing to do with the fault itself. The way the system worked is genuinely clever. The researchers fed continuous daily strain observations into a neural network structure called an autoencoder, paired with something called a wavelet representation of the data, essentially a way of breaking the signal down so patterns at different timescales become visible at once. The autoencoder learned to compress that information into a compact representation, and then the team used unsupervised clustering to sort the results, separating segments of data that looked like genuine ground deformation from segments that were just noise. In plain terms, they trained a machine to recognize the fingerprint of a slow slip event buried inside years of data too dense and too subtle for a human researcher to fully process by hand. That's really the heart of what makes this discovery a story about artificial intelligence as much as it is a story about geology. Human researchers had access to this exact same strain data for years. Nothing about the underlying instruments changed. What changed was the ability to sift through millions of individual data points, hour by hour, across 4 separate stations, looking for a pattern subtle enough that even trained eyes could easily mistake it for noise. A neural network doesn't get tired, doesn't lose focus scrolling through the 10,000th day of relatively uneventful strain readings, and doesn't bring the same kind of unconscious bias toward expecting a particular kind of signal in a particular kind of place. It simply learns the shape of the pattern and then looks for that shape everywhere, consistently, at a scale no team of graduate students poring over charts could realistically match. That's also why the research team behind this study spans multiple institutions with very different specialties. The GFZ Helmholtz Center for Geosciences in Germany brought expertise in machine learning applications to geophysical signals. EarthScope, the organization that operates much of the actual instrument network across the western United States, contributed the deep institutional knowledge of how that hardware behaves and where its blind spots typically show up. Stanford University added decades of accumulated research, specifically focused on the mechanics of the San Andreas Fault itself. It's the kind of collaboration that has become increasingly common in modern seismology, where the biggest breakthroughs often come not from a single new measurement, but from applying a genuinely new analytical lens to measurements that were, in some cases, sitting quietly in an archive for the better part of a decade. What they found changed the conversation. The team identified 92 short-duration slow slip events beneath the Parkfield segment, 21 of which had never been detected before, missed entirely by years of manual inspection using traditional methods. 14 of these newly identified events were independently confirmed, using nearby creep meters, instruments that measure surface movement directly across the fault, which mattered enormously for credibility. When a signal shows up on one instrument, it might be a malfunction or interference, or some unrelated environmental noise. When the same signal shows up simultaneously on a completely different type of sensor, using a completely different measurement method, that's strong evidence you're looking at something real. The researchers went further, reconstructing the location and direction of the slip for these events, and found the movement occurred at shallow depth and was consistent with right lateral motion, the dominant style of slip on the San Andreas, where the Pacific plate moves northwest relative to the North American plate. In other words, this wasn't some strange, unrelated phenomenon showing up near the fault. This was the fault itself, moving in exactly the direction physics would predict, just doing it quietly instead of violently. Then came the part that pushed this from an interesting technical discovery into something with real implications for how scientists think about earthquake risk. The team compared the timing of these newly detected slow slip events against something called low frequency earthquakes, a special category of weak seismic signals associated with deep fault slip processes, distinct from the ordinary earthquakes most people are familiar with. What they found was that low-frequency earthquake activity consistently increased following the occurrence of a slow slip event. The silent movement wasn't happening in isolation. It appeared to be actively modulating seismic activity around it, nudging the surrounding fault system, changing local stress conditions in ways that showed up afterward in the seismic record. That single finding is the reason this research matters well beyond a narrow academic debate about instrumentation. If small, quiet episodes of aseismic slip can measurably influence subsequent seismic behavior, even in a limited, localized way, that reshapes a basic assumption that has underpinned earthquake hazard models for decades, the assumption that strike-slip faults like the San Andreas primarily store and release stress through sudden ruptures alone. Slow slip isn't a footnote anymore. It's a mechanism that appears to be actively part of how this fault redistributes pressure along its length. It's worth pausing here to be precise about what this discovery is and isn't, because a lot of confusion tends to spread the moment a story like this reaches the wider internet. This was not a live, real-time event that suddenly appeared on monitoring screens last month. The slow slip signals identified in this research came from archived strain data collected between 2009 and 2016. Analyzed retroactively using a modern deep learning system that simply didn't exist in a usable form back when the data was first recorded. This is a story about a machine finding something buried in history, not a story about something new physically happening beneath California right now. That distinction matters, and any accurate account of this research has to be honest about it. It's also worth being clear about what the discovery does not prove. It does not mean a major earthquake is coming soon. It does not provide a predictive timeline for the southern San Andreas, the segment most people mean when they talk about the so-called big one. Scientists working on this research and researchers reviewing it from the outside have both emphasized that these Parkfield signals, while robust and well confirmed across multiple instrument types, are geographically limited to a specific stretch of fault known for unusually frequent, moderate seismic activity. Whether similar hidden slow, slip behavior exists on the more dangerous, fully locked segments of the San Andreas to the north and south is a separate, unanswered question, one that will require finding comparable signals in other locations and modeling their effects in detail before anyone can responsibly rewrite statewide hazard calculations. That kind of careful, incremental caution is actually the most reassuring part of this story, even though it might sound less dramatic than a viral headline. Scientists have already begun discussing the follow-up work these results demand, including sessions built around exactly this question at Parkfield-focused research meetings hosted by the Southern California Earthquake Center, and further discussion planned at broader regional workshops focused on earthquake hazards across Northern California. Nobody involved in this research is treating it as a finished story. They're treating it as an opening, a new tool that reveals a previously invisible layer of fault behavior and a new set of questions that now need answers. To really appreciate why this shift matters, it helps to understand what the San Andreas actually looks like when you break it into its major sections, because it does not behave the same way from end to end. The central portion of the fault, the stretch that runs through and around Parkfield, is what geologists call a creeping segment. Instead of locking up and storing enormous amounts of strain for a single massive release, this section slips more or less continuously, offsetting curbs, fences, and roadways in slow motion over years, and producing the moderate, relatively regular earthquakes that gave Parkfield its nickname. It's precisely this behavior that made Parkfield useful as a natural laboratory in the first place, a place where scientists could study fault mechanics up close without waiting decades or centuries between major events. North and south of that creeping section, the fault behaves very differently. To the north, it runs up through the Santa Cruz Mountains, the same segment responsible for the 1989 Loma Prieta earthquake, a magnitude 6.9 event that killed 63 people, collapsed part of the Bay Bridge, and brought down a section of elevated freeway in Oakland during the middle of a televised World Series game, a moment that reshaped how an entire generation of Americans understood earthquake risk. From there, the fault continues through the Bay Area itself before reaching its northern terminus near Cape Mendocino, where it meets one of the most geologically complex junctions on the entire West Coast. To the south, the fault transitions into segments researchers have identified as fully locked and critically stressed, running down through the Carrizo Plain, where you can still see the offset in the landscape left behind by the 1857 rupture, a scar in the earth visible. From satellite imagery to this day, that southern portion has now gone more than a century and a half without releasing its accumulated strain in a major event, a silence that in seismology is not reassuring, it's the opposite. Fault segments do not forget the strain owed to them, they store it, waiting. A separate but closely related study published in 2026 adds another layer to this picture. This one focused specifically on that stressed southern section. Using a detailed physical model built to estimate stress accumulation over roughly 1,000 years, researchers found that portions of the southern San Andreas are currently under more stress than at any point in that entire modeled history. The same study identified a location known as Cajon Pass as what researchers are calling an earthquake gate, a structural point where a rupture on the San Andreas could potentially jump onto a neighboring fault system, the San Jacinto Fault, turning what might otherwise be a single fault rupture into a larger, more complex multi-fault event. This is a different research group working on a different mechanism than the Parkfield slow slip study, long-term stress accumulation, rather than short-duration silent slip. But together, these two lines of research paint a picture of a fault, a system that scientists are actively re-examining with tools and techniques that simply weren't available a generation ago. An earthquake gate, in this context, is essentially a structural weak point or geometric bend where a rupture traveling along one fault has a real chance of stepping across onto a neighboring one, rather than stopping where the original fault ends. Historically, that kind of jump between separate fault systems has been one of the harder scenarios to model with confidence, because it depends on subtle details of geometry, depth, and stress orientation at the exact point where two faults come close together. Identifying Cajon Pass as a likely candidate for that kind of jump doesn't guarantee it will happen during the next major rupture. But it does give emergency planners and structural engineers a more specific scenario to model against, rather than relying purely on single fault rupture assumptions that may understate how large and how complex a future event could actually become. None of this changes the basic, uncomfortable math that has defined California earthquake planning for decades. Hazard models, built by the United States Geological Survey, estimate the probability of a magnitude 6.7 or larger earthquake occurring somewhere along the California fault system at roughly 75% over the next 30 years, with individual segments of the San Andreas carrying some of the highest probability of any fault in the state. A comprehensive modeling study known as the Shakeout Scenario, produced by the USGS in partnership with dozens of research institutions, estimated that a major rupture along the southern San Andreas, somewhere in the range of magnitude 7.8, could cause close to 1,800 deaths, more than 50,000 injuries, and roughly $213 billion in economic losses, driven heavily by fires that follow the shaking and the collapse of older buildings that predate modern seismic codes. To put those numbers in perspective, 30 million people live within roughly 50 miles of the San Andreas Fault system, spread across some of the most densely populated urban corridors in the country: Los Angeles, San Bernardino, Riverside, and the string of communities stretching through the Inland Empire all sit close enough to a southern segment rupture that the shakeout scenario describes the potential damage as catastrophic rather than merely severe. That is the backdrop against which every new scientific finding about this fault has to be understood, not as an isolated curiosity, but as one more piece of information layered onto an already enormous, already well-documented risk that regional planners have been preparing for, in one form or another, for generations. Scientists want to be very clear about one thing whenever a story like this circulates. None of this new research allows anyone to predict exactly when a major earthquake will occur. The United States Geological Survey's own position on this has not changed. Earthquakes cannot be predicted to a specific day, week, or even year using current science, and slow slip data alone does not provide that kind of forecasting power. What this new research does provide is something different and, in its own way, more valuable, a far higher resolution picture of how stress actually moves through a real fault system in something closer to real time, rather than relying purely on historical averages and models built from incomplete information. Every additional layer of understanding like this makes the underlying hazard model sharper, even if it doesn't produce a countdown clock. It's also worth remembering that this entire discovery only exists because of decades of unglamorous, patient infrastructure investment. The dense instrument network around Parkfield wasn't built for this specific breakthrough. It was built starting in the 1970s and 1980s by researchers who suspected that a moment like this would eventually come once the right analytical tools caught up with the sensors already in the ground. The Plate Boundary Observatory Network alone operates more than 1,100 continuous GPS stations across the western United States, many clustered, specifically along the San Andreas system, tracking ground position to within a few millimeters on an ongoing basis. Borehole strain meters push that sensitivity even further. None of that instrumentation predicted this discovery directly, but all of it made the discovery possible the moment someone applied the right kind of machine learning system to the archive it had quietly been building for years. There's a broader lesson buried in how this story actually unfolded, one that says as much about the state of modern science as it does about the San Andreas Fault specifically. The breakthrough here wasn't a sudden, dramatic event captured live by instruments. It was old data, sitting patiently in a research archive, waiting for computational tools sophisticated enough to extract a signal too faint and too complex for manual review. As machine learning techniques continue to improve, researchers across seismology are increasingly turning back to these kinds of historical data sets, wondering what else might be hiding inside decades of raw measurements collected long before anyone had the tools to fully interpret them. Parkfield may not be the last place this happens. It might just be the first place scientists knew exactly where to look. None of this is a reason to panic, and researchers involved in this work have been notably careful to avoid language that implies an imminent, specific threat. What it is, however, is a legitimate reason to treat earthquake preparedness as something worth revisiting, not because of a countdown that doesn't exist, but because the underlying reality never went away in the first place. If you live anywhere near an active fault system, whether that's California, the Pacific Northwest, or any other seismically active region, this is a reasonable moment to check that you know your evacuation routes, that you have a basic emergency kit stocked with water, food, and a working flashlight, and that heavy furniture in your home is properly secured. California has spent billions of dollars retrofitting bridges, hospitals, and older unreinforced buildings since the Loma Prieta earthquake in 1989, and the Northridge earthquake in 1994 exposed serious vulnerabilities in structures built before modern codes existed. The state's early warning system, Shake Alert, now covers the entire West Coast and can provide anywhere from a few seconds to nearly a minute of warning before shaking arrives at a given location, enough time to automatically slow trains, open fire station doors, and give people a chance to drop, cover, and hold on before the worst of the shaking hits. None of that infrastructure prevents an earthquake from happening. All of it exists to reduce what happens once one does. So where does this actually leave us? Scientists spent decades believing strike-slip faults like the San Andreas released their energy almost exclusively through sudden, violent rupture. New research, built on 9-year-old data and a modern artificial intelligence system nobody had access to when that data was first collected, has shown that assumption was incomplete. The San Andreas doesn't only break, parts of it also creep quietly in ways that measurably influence the seismic activity happening around them. And researchers only found this because a machine finally learned how to listen closely enough to hear it. That doesn't mean anyone can tell you when the next big earthquake will strike. Not this year, not next year. Not on any specific date anyone could responsibly put on a calendar. Nobody can, and anyone claiming otherwise isn't practicing real science, no matter how confident they sound doing it. What it does mean is that the picture scientists are working from just got a little more complete and a little more honest about how much complexity was hiding in plain sight the entire time. Researchers are already following up, comparing these findings against other stretches of the fault, testing whether similar silent signals exist in the segments capable of producing genuinely catastrophic earthquakes, and presenting their results at the same regional workshops, where this kind of foundational science gets stress-tested by the wider community before it ever reshapes an official hazard model. That process is slow, it's careful, and it's the opposite of the instant certainty a headline promises, but it's exactly the kind of process that keeps earthquake science credible in a media environment that often rewards the opposite. We will keep watching this research as it develops because the story of the San Andreas Fault isn't finished, and after this, the way scientists read it never quite goes back to what it was before.